In a balanced chemical equation, the formulas can represent atoms, but they can also represent larger quantities, such as a mole. In this equation right here, I have a mole to mole ratio of 2 moles of water to 2 moles of hydrogen to 1 mole, which is the one is not written, of oxygen. We can use these molar ratios to help with converting. Let's do this first problem. Start with a number that's given. We have 7 moles of water, and we want to convert to moles of oxygen. And we're going to use the balanced chemical equation to help us with the ratio. It's kind of like a recipe. So in the equation, we have 2 moles of water to 1 mole of oxygen. So that's our recipe of 2 to 1. You want to make sure that you line everything up correctly, so writing your units is very important. I want to cancel out moles of water and change it to moles of oxygen. And I'm going to put in the ratio. The ratio is a 2 to 1 or 1 to 2 ratio. It's important that the moles of water goes down at the bottom so that you can cancel the unit you're starting with, the 7 moles. So moles of water cancels, and I'm left with moles of oxygen. You need to be in moles to be able to use the balanced chemical equation. So sometimes we start with grams of a reactant or a product, and we need to first change it to moles, apply the mole ratio, and then change it back to grams. So the pattern would be grams to moles to moles to grams. So starting with 8 grams of water, I'm going to first change it to moles. So grams is going to go on the bottom and moles on the top. And I know that 1 mole of water gives me 18 grams of water. That is our conversion factor. I get this from the periodic table. Next, grams cancels. I'm left with moles of water. And now I'm going to apply my molar ratios. 2 moles of water to 1 mole of oxygen. And I get that from the balanced equation. Moles cancels, but so does the water, and I'm left with moles of oxygen. The next step is to convert from moles of oxygen to grams of oxygen. And I'm going to get the molar mass or the molar weight from the periodic table. So moles cancels, and I'm left with grams, and we can do our math. Remember, as you go across, you multiply. As you go underneath, you divide, and you should do a zigzag pattern. So 8 times 1 divided by 18 times 1 divided by 2 times 32 divided by 1. And the answer that I get is 7.1 grams of oxygen. Notice the conversion factors. These two things are equal. 18 grams of water is equal to 1 mole. These two things come from the balanced equation, and it's the molar ratio of 1 to 2. And these two things are equal. 1 mole on the periodic table is equal to the molar mass added up. And I have 2 oxygens, so I add those up. Limiting reactants. Reactants are always in excess to ensure that sufficient product is produced. If you have 2 reactants, there will always be one that runs out before the other one. The one that runs out first, that is called the limiting reactant. I am limited in the amount of product that I can make by that limiting reactant. So how do we determine which is the least in the reactant? And the answer to that is we need to convert to moles. We're going to convert to moles, but we are also going to do the conversion process twice. And you can stop at the moles step. So what I mean is you can stop here. You can do grams to moles. But I find it helpful to go all the way to grams because typically they will ask the amount of product in grams that you can make. So you might as well just do it in the first place. So I have my balanced chemical equation up here, and I have some starting amounts. So I find that there is 10 grams of water, and I have 16.8 grams of iron. Now you can't just look and see which one's going to run out first. It's a good idea to back it up with math. And in AP chemistry, backing something up with math is proof that you know that one is the limiting reactant. I'm going to pick one product to compare to, and it really doesn't matter which one you do. I do have this problem set up so that we're going to compare both the iron and the water to this iron oxide. But you could do the hydrogen. The reason why I picked that product is because it says how many grams of iron oxide can be obtained. So usually the product that we're going to convert to is something that is a value or is easy to be measured. And we can see that the hydrogen is a gas, and that's just a little bit more difficult to catch. So it'd be easier just to measure your solid that is formed at the end of this reaction. So let's go ahead and compare and figure out which of these reactants, the iron or the water, is the limiting reactant. Which one's going to run out first? So I'm going to start with the 16.8 grams of iron, and I'm going to convert to moles. In order to switch to products, I need to be in moles so I can use that molar relationship. I'm going to look at on my periodic table, and I'm going to see that iron, there's 55.8 grams of iron in 1 mole of iron. Grams cancels, I'm left with moles. Now I can use my molar ratio. I have 3 moles of iron for every 1 mole of the iron oxide. So my moles is going to cancel, but also my iron's going to cancel, and then I'm going to be left with moles of the iron oxide. And I know that 1 mole of the iron oxide is equal to 231.5 grams. I get that from right here, they tell me. Doing my math, I get 23.2 grams of that product. Now we're going to repeat everything over, but this time starting with the water. Again, using the periodic table, I find that water is 18 grams. 2 hydrogens and 1 oxygen equal 18, and that's equal to 1 mole. Grams cancels. Now I'm going to use the ratio found in the equation. 4 moles of water goes down here, so I can cancel it. And up above, I have my 1 mole Fe3O4. Moles cancels, and also the water cancels. And then just as before, there's 231 grams in 1 mole of the iron oxide. Doing my math, 10 times 1 divided by 18 times 1 divided by 4 times 231.5, I get 32.15 grams of that iron oxide. So which of these is a limiting reactant? Well, it's the one that makes the least product. So iron is the limiting reactant. This is the one that occurs. This one is like the fake one. It's not going to happen. The reason it's not going to happen is because my iron's going to run out way before I can use up all the water. So the water's in excess and the iron is the limiting reactant. This asks how much of the excess reactant would be left over. So you're going to use the limiting reactant to compare. So I'm going to start with that iron. Now that I know this is my limiting reactant, I'm going to see how much water will be used up. So looking on the periodic table, there's 55.8 grams of iron to 1 mole. Grams cancels, I'm left with moles. This time I'm going to compare the two reactants. So 3 moles of iron to 4 moles of water. Moles cancels, but also the iron cancels. And then I know the conversion is 1 mole of water is equal to 18 grams of water. And I get this gram amount from the periodic table. Doing my math, I get 2.77 grams of water is used up. So if I started with 10 grams of water, and I know that 2.77 grams is used up, then what is left over is 7.23 grams. This is the leftover. So knowing a starting gram amount, I can convert it to any other reactant or product. These are all theoretical numbers. In the lab, it would be a little bit different. In the lab, we generally get less than what our calculations tell us. Our calculations are the theoretical yield, the ideal, and we never get the ideal. Instead, we get less. The reactions, the collisions that occur during the reaction, they're not 100%, and as a result, you get less product. So let's look at this equation here. This is our percent yield equation. If the theoretical yield calculated for a reaction is 14.8 grams and the amount of product is 9.25 grams. What is the percent yield? So we have what our math says I'll get. This is our theoretical. And then we have actually what our lab is. This is our actual. So we just take our actual and divide it by our theoretical, what our math says, times 100. And in this case, we get 62.5% yield. So this is lower than I actually like to have it. In our lab, I like to have at least 80. So we might have to look at the procedures and see what's going on. Maybe we need to warm up the reaction a little bit so the collisions are better. Maybe we need to make sure we've taken our measurements correctly. But in the lab, you'll always get less.